It's my great honor to speak at CMSA. Yeah, so today I will talk about degenerate Monge-Ampère equation and the variational approach via mismeasure and monotonicity. Let's see. All right, so the equation that we will study is quite classical. It had been studied for more than 200 years in various settings. So especially it's also appear in the gap curvature equation, in the surface tension in dimer model in combinatorics and mathematical physics. It also appear in special Lagrangian equation that Yang Li talked in the morning, and it's also appear in the optimal teleportation that Robert talked a few hours ago, and also appears in meteorology. And so the setting that we consider had three information on the data. We have a Borel measure nu on the boundary convex domain omega and In, and we have perimeter P, which is negative. And we consider this Monge-Ampère equation with the right-hand side of this form and zero boundary data. And so the unknowns are the convex function U and the constant lambda. And so that's the unknown. All the information are data. And so we will only consider convex solution of this equation. Of course, there's a question about whether there are non-convex solution. That's a very interesting problem. We don't know much about that. And as you can see, zero is a solution to this problem. And so therefore, the interest is to study non-zero solution. Okay. And so by scaling or homogeneity, when P is different from N, then both sides scale differently in terms of U. And so therefore, when P is different from N, we can always take lambda equal 1 if we can find such a solution to our equation. All right. And so this is the standard notation, the square Q to be the Hessian matrix of our function U. And so we will talk about convexity a lot on this talk. And so when U is a C2 convex function, then the Hessian is the negative definite matrix. So this is the plan of the talk. So I will give a very quick review of previous results and methods. And then I will talk about solvability and uniqueness of this equation. And so I will not talk about regularity. That's a very interesting subject, but this because of time. And also I will mention about the methods and the tools. The takeaway from the talk is that if we look at this equation, then this equation is solvable when the measure nu is integrable when we integrate against the distant function to the boundary. And so in this sense, the measure nu can be very singular at the boundary. And moreover, when P is bigger than N, we can allow nu to be more singular. All right, so when nu is the Lebesgue measure, our equation becomes this form. And so as you can see, when P is bigger than 0, and the right-hand side here tend to 0 when we are approaching the boundary. And so therefore, our equation becomes degenerate. Moreover, there are many situations where we can encounter this kind of equation, especially when P is equal to N-1. It appears in the prior estimate for the upper equation in CSCK metric in the work of Donaldson. And when the particular case that we pay more attention will be the case when P is equal to N. So that's the case of the Monge-Ampère eigenvalue problem, which was initiated by Lyon. We're not going to talk more about that. And recently, there's many works related to the Calabi-Yau metric in the works of Colin, Tong, and Yau, where they study problem of similar flavor. All right, so let's recall the results of Lyon's that were proved about 40 years ago. So Lyon considered the case when the domain omega is smooth and uniformly convex. You can think like something very close to a ball. So he showed that there is a unique constant lambda depending on the domain omega, and a unique non-zero convex solution U solving the Monge-Ampère eigenvalue problem. the constant lambda here is called the Monge-Ampère eigenvalues of the domain omega. And the convex function U is called the Monge-Ampère eigenfunction of the domain omega. And so the constant lambda is unique, but the function U solving this problem is unique up to multiplicity constant. Because of the homogeneity of both sides, if any U solving this equation, then any positive multiple also solve the same kind of equation. All right, and so that's the uniqueness. So I must mention in passing that Leon also showed that it's smooth in the interior, and then let's see when we went up to the boundary. Okay. All right, so usually I will not do a lot of proof in this talk, but I would like to mention the proof by Leon because it's kind of a universal proof because it's applied to many other situations. The equation here is degenerate at the boundary, and so therefore Leon relies on the non-degeneracy result of Gaffron, Nienberg, and Spratt, where they study Monge-Ampère equation without a lot of degeneracy. And so the way Leon is going to look at this kind of Monge-Ampère equation, where the right-hand side here, you see that when t is equal to 0, it's just number 1. And so therefore, because our domain is 9, and then you can solve at least for t equals 0. And after that, the linear operator is positive definite. You can use the implicit function theorem to move a little bit beyond 0. And so you can stop solving more and more for t positive until you stop. And when you can, and you stop, then that's why when you get the Monge-Ampère eigenvalue. So that's the methods. And it turns out that this method works for all varieties of fully nonlinear PDE, including the K-Hessian equation in the real K by Suya Wang, and also in the complex K by Zhu Liu and McCleary. And it also works for the complex Monge-Ampère or also work for hyperbolic operator. And so the Monge-Ampère is one particular of the many family of operator that you can solve by this method. And so somehow this method is kind of very universal. So then a few years after the work by Leon, used parabolic Monge-Ampère equation to find a variational characterization of the Monge-Ampère eigenvalue. So he found that the Monge-Ampère eigenvalue is given by the infimum of the Borel quotient related to the Monge-Ampère operators among all convex functions U, which ellipses up to the boundary, 0 at the boundary, and then C2 in the interior. And so you can see that this is very similar to the Borel quotient for the Laplace operator, because if you replace the determinant of Hessian of U by the Laplace operator and you integrate by part, then the numerator will become the Dirichlet energy. So of course you see that this power here is different from the case of the Borel quotient for the Laplace eigenvalue because of the homogeneity. We want the quantity here to have a 0 decrease in U. And so the n plus 1 power here is the correct power. All right. And so moving beyond the K and P is called n, so also show that actually for any P bigger than 0 and different from n, you can also find a convex, non-zero convex solution to this equation. And of course, it's C infinity in the interior and leaves it up to the boundary. And so also show that when P is smaller than n, the solution found here is also unique. So this is different from the case of the Monge-Ampère eigenfunction, where you're unique up to the multiplicity constant. All right. So after the work, so we may wonder what happened when the domain is just convex, because problem for Monge-Ampère equation with 0 boundary condition, then the domain is just the 0 sublevel set of the convex function U. So we wonder what happened if we consider the problem on the general boundary convex domain. And so using the approximation argument and Caffarelli regularity techniques, I was able to extend the result of Leon and so to the general convex domain. So in this new extension, we encounter two new tools that we might encounter again later in the talk. So the first one is called a nonlinear integration by parts. And this the new phenomena here about the global ellipses will not be discussed later on, but It's so that when we would like to compare with what so this for the smooth and uniform convex domain, then it turns out that in this case, if we would like to have the global ellipsis of the solution for general convex domain without any regularity, then we can only guarantee the global smoothness, the global ellipsis for the solution when P is bigger than this threshold. Other than that, we can show that it's not global ellipsis. All right. And so similar to what showed this, there was two characterization of the Monge-Ampère eigenvalues. So the second one is very similar to so. This is exactly so, but it will prove much later. It just proved last year. The first one is different, but it will prove much earlier. So in the sense that in the first one, we consider the set of comparator which is larger than the one that showed this. The result of so consider the set of comparator to be global ellipsis up to the boundary and C2 in the interior, of course 0 on the boundary. But in this result here, we just consider in the bigger set of comparator. The set of comparator consider all convex function 0 on the boundary. And so therefore, when we consider the bigger set of comparator, the convex function may not be C1. And so therefore, we don't have we have to replace the determinant of the Hash-U by a proper quantity. That is exactly the Monge-Ampère measure of a convex function U that I will recall in a moment. Anyway, so many things have been done very similar to for the smooth and uniform convex domain. There's one thing that is still very quite open when they say what happened to this equation when P bigger than n. So do we have uniqueness of a non-zero convex function solving this equation? And so it's still wide open, and there's some recent process by Wang and his co-author, but I think it's still wide open. All right, so we will encounter the Monge-Ampère measure later. So I would like to recall it. Instead of using the standard subgradient, I would like to mention maybe some kind of properties. Maybe that's easier to understand in case you haven't seen it before. And so what is the Monge-Ampère measure of a convex function U? So when U is a C2 function, then this Monge-Ampère measure is absolutely continuous with respect to the Lebesgue measure, and the density is given by the determinant of the Hash-U. On the other hand, for any function, convex function, you can use convolution to approximate by C2 function, and for C2 function, you can have the Monge-Ampère measure again. And so the point is that if you have the conversion of a sequence UK to U converge locally uniformly, then the Monge-Ampère measure converge weakly. So this is the way that you can define for any convex function U without using the subgradient. Okay, and another property of the Monge-Ampère measure is that it's a Borel regular and finite on compact subset of omega, and so therefore it's a random measure. And so the point is that you might have trouble with the mass at the boundary, but in the interior, it had finite local mass. Okay. And so now we will look at the degenerate equation when nu is a general Borel measure. This kind of setup had been studied very recently. The first work by He and Wang, where they studied the Monge-Ampère eigenvalue problem with interior integrable singularity. So they have at the boundary, everything is nice, but in the interior, the measure nu is given by a density which is going to infinity, but the density is integrable. And right after that, there's a work by Liu and Zirahi using complex Monge-Ampère technique to study this problem when P is either 0 or B is equal n. When B is equal 0, we had the Dirichlet problem. And when B is equal n, we have the Monge-Ampère eigenvalue problem. And so one point we would like to mention in the work of Liu and Zirahi is that when they study the Monge-Ampère eigenvalue problem, they study in the finite energy class. That's in the complex setting, but I will give a very quick definition in the real Monge-Ampère setting in a moment. the point of the work by Liu and Zirahi is that they first solved the problem using complex Monge-Ampère technique that had been developed for the last 20 years, and after that passed from the Monge-Ampère equation to the real Monge-Ampère equation using the connection between the two via the log map. I think Zhang Li also used the connection in the talk this morning, and so the connection can be found in the work of the authors. All right. And so what are the conditions in the work of Liu and Zirahi? So the condition, of course, there are other conditions, but I state the simplest one as is almost optimal. So in the sense that they need that the measure nu is integrable when you test again the absolute value of a convex function V, and which is negative in the interior. And so how to understand this condition and their work? So because because V is negative and convex, so therefore, if you are away from the boundary, then the absolute value of V grow like the distance function of the to the boundary. And so therefore, this condition implies that nu is integrable when you test again the distance function. And so this is exactly the setting that we will focus on. All right. And so for simplicity, we can think about, well, when you are following the talk, you can think about nu has density like the negative power alpha of the distance function where alpha is smaller than 2. I might come back to this example again because I will say a few words what happens when alpha is 2, exactly. All right. Okay, so we saw that, so coming back to a degenerate Monge-Ampère equation, we saw a lot of interesting work when p is equal 0 and p is equal n using complex Monge-Ampère methods. And so I come from the real Monge-Ampère equation, so I would like to say, what can we do if we just consider this equation in the real Monge-Ampère setting? And furthermore, what can we say about the solvability and uniqueness when p is bigger than 0 in general, because the work by Liu and Zirahi or He and Wang only consider when p equals 0, when p equals n. They don't consider the p in between. All right. And so for the rest of the talk, I will mention how to use the real Monge-Ampère methods to solve this equation, and the way to do that is via mixed Monge-Ampère measure and monotonicity. So we developed some technique along the way, and the techniques allow us to treat the nonlinear Monge-Ampère operator like a linear one. And so you will see a lot of argument that you can see the analog in the linear setting. So we will try to do that for the nonlinear Monge-Ampère equation. So by the way, so there are many technique results that I will mention that have a complex analog, but the ways that we don't see a lot of written up in the real Monge-Ampère setting. So I think the last part of the talk will be mostly expository. Yeah, but I think that's also helpful to see what it needs and so and what can be developed further. All right. So as mentioned in the work of Liu and Zirahi, they need to consider the Monge-Ampère eigenvalue problem in the finite energy class. So here we consider the real Monge-Ampère setting. And so first of all, we define the energy, Monge-Ampère energy of a convex function. So we integrate the Monge-Ampère measure of U via negative U. So that gives the energy. Because the negative one is the following. So when U is 0 and is convex, then it's a negative in the interior, so negative is actually the absolute value of U. And so the finite energy class we denote by capital E consists of all convex functions vanishing on the boundary and convex in the interior with finite Monge-Ampère energy. So this is the definition of the finite energy class. Okay.
So you said it, but you're not assuming U has a sign, do you? Or?
So in this case, when we talk about Monge-Ampère energy, we don't need any sign of U, but usually when we apply for it, so it already U is negative in the interior.
So U is 0 on the boundary.
Yes, so in this one. So script is U already 0 on the boundary. That's right. Thank you for the question. Okay, so I think maybe we can just skip this definition and we go straight ahead to the definition over here, because that's how we define the Monge-Ampère energy. Okay. All right. So let's state the result about the solvability of a degenerate Monge-Ampère equation. So actually, we can do further with the real Monge-Ampère methods. We can consider P to be negative, bigger than -1. So in this case, we have not only we have the singularity of the right-hand side. And so what are the assumptions on the Borel measure? We consider the Borel measure, of course, the condition just say that it's non-zero. And it has certain integrability condition. And this integrability condition depends on the distant function raised to a certain power. And we see that the bigger the P, the smaller the quantity. And so therefore, the more singular we can allow for nu. But when P is very small, let's say when P equals 0, so this power is 1 over n plus 1. So we integrate a larger quantity. So somehow we require nu to be more regular at the boundary when P is small, but we can allow it to be quite singular when P is large. So that's the condition over here. So what we can do, we look at these expressions then over the finite energy class, and we look at for the minimizer of it, and then actually we can find a non-zero minimizer, and the non-zero minimizer solving degenerate Monge-Ampère equation. So that's the first statement. The second statement is about what happened when, in this setting, when P is equal to n. So in this case, we have the Monge-Ampère eigenvalue problem. And so actually this result also recover, and it's the same equivalent to this result by Luz and Zirahi. So in this case, we can say more about what we found up here. What we found up here, we can say that actually the constant lambda here is unique. And then the convex function yield, which is the minimizer of the quantity over the finite energy class, is also unique up to multiplicative constant. And so, and moreover, how we can find the constant lambda when P equals n, so it's equal to the quantity which is the infimum of the Rayleigh quotient in the finite energy class. So let me emphasize that in the second statement here, we had a uniqueness result when we are talking about everything in the finite energy class. So I will have a couple of remarks about what happens if you get out of finite energy class.
So you're going to tell us about why it's unique? Or?
I might say why it's unique for lambda, but not for you. So unfortunately, I don't have time to explain that proof. So I can say at least why in the finite energy class, lambda is unique. Yes, thank you. Okay, are there any other questions?
So the first one is also correct?
Sorry?
Number one, first part of the theorem, that's also.
That is a very good question. So unfortunately, I don't know the answer when P bigger than 0, except that when P is from 0 to n and nu has compact support, it's unique. Or when nu has the continuous density, which is strictly positive, is also unique. Otherwise, I can...
But not for all P, right?
Not for all P.
Just for
P is smaller than n. All right. All right, so that's also, I also, during the course of proving the result, there's also another spectral characterization of the Monge-Ampère eigenvalue, because this is given by the Rayleigh infimum of the Rayleigh quotient among the finite energy class function. So this is one characterization that extends the work of Birin, Daly, and Bainey from Lebesgue measure to singular Borel measure is that we can show that the infimum of the Rayleigh quotient equal to the supremum of all the sub-eigenvalue. And so this is kind of equation called the sub-eigen. So whenever we have a function v vanishing on the boundary and convex, and it satisfies these inequalities, the right-hand side here is involving with the measure nu, the left-hand side is involved with the Monge-Ampère measure of V, then we call capital lambda is the sub-eigenvalue. So it's very natural that the eigenvalue should be the supremum of all sub-eigenvalue. Now let me explain very briefly why is the integrability condition that I imposed in the first theorem. So this is the integrability condition we have. And so why is that? Because the methods of proving the theorem is by variational methods. We consider the solution in a finite energy class. And so there's a little lemma that we can show that in a finite energy class, the function V must have these regularities, and it means that it must grow, roughly speaking, like the power 1 over n plus 1 of the distance to the boundary. And so this is, we have one side, and also for general convex domain omega, we can show that it's a sort of optimal result. And so therefore, because in the variational methods, we would like to minimize this expression, then of course, the numerator is finite because we are in a finite energy class, and so we also want the denominator to be finite. So therefore, we don't, and so therefore we would like the quantity to be finite, and so therefore from this regularity is transferred to the quantity. So that's the rough idea. Okay, of course we can improve more, but I think for this first theorem, I just state in that version, and because for P is smaller than n, actually we can allow nu to be more singular. So that's the content of the next theorem. And so when P is smaller than n, actually all we need is that for the Borel measure is that it's integrable when we test again the distant function. And so we see that, let me come back to here. So when P is exactly n, so the quantity here is exactly the distant function. But when P is smaller than n, the quantity here is much bigger than the distant function. And so therefore, in the second theorem, when P is smaller than n, we allow nu to be more singular. Okay. And so under this condition, we can show that there exists a non-zero convex solution U solving degenerate equation. So here I take lambda to be 1 because of the homogeneity. And so let me make a couple of remarks about this theorem. So when P is equal to 0, this problem is just the Dirichlet problem with the right-hand side, the Monge-Ampère measure nu. In the classical result, we usually solve the Monge-Ampère equation when we are required that the right-hand side has finite mass on the whole domain omega. And so that's the general result was done by Blocki and Hartenstein a long time ago. So here we allow nu to be more singular, and so when P is equal to 0, this result is then all the classical result, and also when P equals 0, I would like to mention that this result also done by Le and Ziri. But the result when P is bigger than 0 and smaller than n, so this is new. On the other hand, we might question, okay, so we found a solution. Are they in finite energy class? Because maybe energy class give us one way to do it. Maybe we can find another way. And maybe in the end, it could be in a finite energy class again. And so it turns out that's not. So because exactly when the K when P equals 0, even for the Dirichlet problem, and when omega is a box in all dimensions, and if we just take the measure nu to be any power negative over 4 or anything close to -2, then this problem we can solve because it satisfies the integrability condition, but the solution we found had infinite Monge-Ampère energy. And so therefore, this is different from the finite energy consideration.
Question. So when you work on compact Kähler manifolds, there are other energy classes that people look at, not just some weighted energy. Is there something like this here that you use, or?
So I haven't had a chance to look at the work, but I think this is different methods. And so because I don't believe there's any kind of monotonicity argument in the work. So yeah, so thank you for the question. All right. So and you might wonder, is this condition kind of optimal? of course, as you might see, so here the intuition about this equation, actually this condition we only worry much when p equals 0, because somehow if we look at this equation, because if there is a solution, then somehow near the boundary, the bigger the p, this quantity get, smaller and smaller at the boundary. So somehow it looks like we are in the better shape when b is bigger than 0. But of course, the proof does not tell us that. Anyway, at least when p equals 0 for the degenerate problem, this condition is up to a log factor is optimal. So in the paper that I put out on the archive, so I gave some explicit domain that actually you can only do better by a log factor, but you could not put that any power bigger than 1 over here. Because if you, instead of the power 1, you put the power gamma, when gamma is bigger than 1, then we can find some domain omega, and when we try to solve the degenerate problem had no solution. All right. Are there any questions? So let's talk a little bit about the proof. So for the first theorem, we will use variational methods to solve it. And so we would like to solve it, this equation when the measure nu satisfies this integrability condition. And so as mentioned in the statement of the theorem, we solve this equation by looking at the minimizer of this expression in the finite energy class. And so to prove the existence is not a very difficult process, because now there's a lot of techniques to allow us to do that, so I will skip this one. However, it's more involved to show that the minimizer of the expression actually solves the equation we are after. And so what can we do? So as usual, if we want to show that the minimizer solves the equation, we have to do the variation. And so for the expression in the denominator, it's not that hard, because it's more or less standard. But what is more involved is the expression in the numerator, because that involves the Monge-Ampère measure of the function u. And so if we use a test function phi, then the variation we can think of is to look at variation of the form u plus t phi, when t is a real number and we would like to send t to 0. And so therefore, if we look at this expression in the numerator, then to talk about the Monge-Ampère measure, then usually we need to stay in the convexity class. And so therefore, we could not work directly with u plus t phi. And so therefore, we need to use the convexities. So the closest way to a convex function of u plus t phi is to look at the convex envelope. And so that denoted by gamma. And so therefore, in the end, we have to compute the variational derivative of the Monge-Ampère energy of the convex envelope of u plus t phi when t equals 0. So that is what we have to do. On the other hand, we don't have to look at for all convex functions, because this was a very nice observation by Segrel in the complex setting, that actually for any compactly supported smooth test function, you can write as a difference of two functions which are Lipschitz and in a finite energy class. And so therefore, in this calculation, we only need to restrict ourselves to the case when phi is just finite energy class and has the globally Lipschitz property. All right, so the goal is to compute the variational derivative of the Monge-Ampère energy. And so this is the precise statement. The precise statement says that if you have...
You come back to the previous statement. It was really just a statement about finite energy, right? I'm a little confused. Right, okay. So it's compactly supported, guys.
Yeah, so any compactly supported... So
the phi 1 and phi 2 may not be compactly supported, just their difference is compactly supported.
Yeah, not because they are convex functions that are non-zero. They could not be compactly supported, because compactly supported convex functions are trivially 0.
Okay, good.
Thank you. Any more questions before I talk about computing the variational derivative of the Monge-Ampère energy? All right, so we need to compute the variational derivative of this G plus dV when V is now because of the result of Seaground, we only need to look at the variation along the finite energy class direction. And so this is the formula. So roughly speaking, it said that the Monge-Ampère measure is the derivative of the Monge-Ampère energy. That's what they say in the formula. All right, so in the complex setting, this is a well-known result. It's called the projection theorem in complex Monge-Ampère equation. There are many works that you can see the appearance of this theorem. So for the real Monge-Ampère setting, for the proof, we use the mixed Monge-Ampère measure with fully linearized the Monge-Ampère operator, and then there's also we use the integration by part. So I will go over all the ingredients. So basically, with all the ingredients, so essentially you compute this integral like you are doing the variation of the usual Dirichlet energy. All right, and so what is the mixed Monge-Ampère measure? So
it's sort of heuristically clear, right?
Yeah. Thank you. All right, so what is the mixed Monge-Ampère measure? So suppose you are given the n convex function U1 to UN in some domain in omega n, and we define the mixed Monge-Ampère measure. So I call nu n of in this bracket here. And so how to do that? So there are many ways. So there are two ways. The first way is that we want to retain some flavor of the Monge-Ampère measure, because later on when we would like to do anything about compactness or about continuity, so one way is to use the polarization and the Monge-Ampère measure. And so this is the formula. So basically it is sum of the size sum of certain Monge-Ampère measure of certain combination of these U1 and UN. But that does not explain the linearity, because we want something that the measure here we want is have the multilinearity for our calculation. And so therefore there's also another formula when all functions are C2. And so in that case, we can have a representation formula for the mixed Monge-Ampère measure via the second derivative of the involved function. And so this formula, you see, involve the Kronecker symbol, so we don't have to worry about that. But the point is that this formula allows us to see the linearity in each slot of the mixed Monge-Ampère measure. And so with that, there's a little work that we can show that for convex function U1 to UN, then the mixed Monge-Ampère measure is a negative Borel measure and is invariant under permutation. Of course, you can see it from here too. And also when U is a convex function, then the Monge-Ampère measure and the mixed Monge-Ampère measure of all n copy of n of U are just exactly the same.
Sorry, your Kronecker delta, does it take both sides? I'm a little confused.
Yes, it's both sides. So in this case, when you, so if I1 to In is different from the triple J1 to Jn, then this gives you 0. But and if they are the same, and it depends on whether you are with odd permutation or even permutation, odd give you -1, even give you 1. All right, and so when we fix n-1 slot and we just vary the last one, then this mixed Monge-Ampère measure is nothing but the linearized Monge-Ampère operator that should be in other contexts. And so the point is that because we have the representation in terms of polarization and the Monge-Ampère measure, and we can have all the stability properties of the Monge-Ampère measure transfer to the mixed Monge-Ampère measure, and so therefore we also have the stable under local uniform conversion of each slot in the of U1 to UN. All right. And so in order to do that, we need one technique that we usually do when we tell our graduate students, if you want to, when stuck with PDE, try to integrate by part. And so that's exactly what we will do. And so what is the integration by part? So we would like to do something for the finite energy class. Suppose that you are given n plus 1 function U0 to UN in a finite energy class, and we want to integrate by parts. So what does it mean by integration by parts? So let's look at the quantity on the left-hand side. Then we see that we have the Monge-Ampère measure of and convex function U1 to UN. So think about all the functions as C2 functions. So therefore, we have to compute two derivatives of each of the function. And so therefore, if we look at the integrand here, U0 had no derivative involved. And so the way is that we want to exchange one slot inside here out, and we want to put U0 in. So it means that we want to put more derivative into U0 and take some derivative from, let's say, UN out. And so this is kind of, we have the same expression, we just interchange the derivative from this quantity to the other quantity. So in this case, actually, we are interchanging two derivatives from UN to U0, and we want to do one at a time.
Sorry, I've forgotten the energy class, but the energy class forces the Dirichlet boundary condition, right?
So the zero boundary condition and convex, and this energy is finite. All right. And so, first of all, so it turns out that when all the functions involved, we can do the finite, all the functions involved are in the finite energy class, then we can have the integration by part formula. And so this is kind of natural, the finite energy class is natural in the following sense, because before we want to integrate part, we want to make sure that the quantity we consider are just finite. Because what happens when they're not finite? Of course, the mixed Monge-Ampère measure here is negative, but U0 is negative here. So actually, the quantity we should put is look at the absolute value here. And it turns out that this expression is finite because there also something called the generalized Cauchy-Schwarz inequality. We can bound this integral via the Monge-Ampère energy of each of the individual functions. And so that's guarantee the finiteness of the quantity we consider down here. And so therefore, the takeaway for this theorem is that we have the integration per part formula for mixed Monge-Ampère measure with function involved in a finite energy class. All right, this is well known in the complex Monge-Ampère because the first generalized Cauchy-Schwarz inequality, I think, equal first proved by Person, and after that, for the integration per part formula, we will prove by Segrel. But I think so the interest here is in the real Monge-Ampère setting. All right, so we will not go into prove this theorem, but let's say this, how to prove something like this. In general, we will work with Variational function. And so therefore, if all the functions are nice, then we can compute this mixed Monge-Ampère measure by using the second derivative, and then this is just the usual integration by part. But our setup do not allow that, so the best way is to use approximation by uniformly convex function. And so actually there's a tool to do that by Lemmer, by Hartenstein. Roughly speaking, they say that if you have a finite energy class function U, then you can approximate it in the L infinity norm and also in the Monge-Ampère measure by a nicer function, which is C2 in the interior, 0 on the boundary. And then if the boundary is nice, then actually we can choose V to have better regularity. And so therefore, in the end, we do two steps. The first step is to prove the this inequality, equality for the domain omega to be smooth and uniform convex, and after that we approximate the function, the domain by any bounded convex domain by smoother domain, and for bounded convex domain we can also approximate the finite energy function U by better ones.
So you keep the boundary condition 0, or
so
when you approximate?
When we approximate, if when for function, we keep the boundary 0, but for different domain, we have to do, so we could not approximate, so we work on the problem, we consider the energy in the approximating problem and back to the limit. So because somehow for this one, if we approximate the domain, then if we keep the boundary condition, then usually it's violated the convexity. So we have to, but for each approximating domain, we have the same zero boundary condition.
So this theorem of yours is sort of it's a real analog of these older theorems from the complex setting. Is that right?
That's right. But I believe the proofs are quite different.
Right, but I guess what I meant here, you're not fixed, you're not changing the domain, right?
This is not change the domain, we
Okay,
change the
right.
function.
Right.
But
But the new function, does that have zero boundary conditions?
this function V here,
Yeah.
it also has zero bound condition
Okay,
here.
that's
Yeah,
good, that was
yeah,
my question.
yeah. All right. Okay, so maybe I will just give the flavor of how to prove the projection theorem or the formula for the variational derivative of the Monge-Ampère energy. So we would like to go to the theorem that we would like to prove it is. Okay, so I will not prove it the full version. I will prove for the right-hand side, the right-hand limit, because when the right-hand limit, when we look at t positive in here, and we see that u plus dv is already convex, so we don't have to give any convex envelope. So at least go on one side. I can tell you what the idea involving one side, because the other side has more involved work. But I think all the ingredients are almost the same. All right, so how to do that? So first of all, the finite energy, so the integration by part formula in the finite energy class allow us to factor the difference between the Monge-Ampère energy up to function in the finite energy class. Because somehow the way we see that whenever we have the Monge-Ampère measure, mu of u is the mixed Monge-Ampère measure of all n copy of it. And so therefore, this one, we subtract this one. So somehow it looks like you can imagine formulate the left-hand side is like v to the n plus 1 minus u to n plus 1. So you can have the factorization formula. And so therefore, this is exactly this. So we can have, but the point is that we don't see the mixed Monge-Ampère measure on the left-hand side, but on the right-hand side, because we have to interchange one entry at a time. And so therefore, we have to use the mixed Monge-Ampère measure. So this is a fully linearized process. So therefore, if we would like to compute the right-hand derivative formula for the Monge-Ampère energy, so this is the expression we want to compute when t is positive, and u and v are functions in the finite energy class. And so therefore, we can apply this factorization formula. And so we have this short calculation given by the expression. And so we would like to have the quantity that we are interested, because we want to pass the limit, we want to get this quantity. And so by factoring this factor out, what is left is this. And so there's a bunch of terms, but the point is that each term in the mixed Monge-Ampère measure, it just involves either u plus dv or v or u, but all the terms we can use the Cauchy-Schwarz inequality control because u and v had the finite energy. And so therefore, if we use Cauchy-Schwarz, the mixed Monge-Ampère measure here, each term is just finite. And therefore, but there's a factor t outside, so we can send t to 0, and so this term will go to 0. And so this proves the right-hand derivative formula when t is positive. All right. So now I think Robert asked the question, how to prove the uniqueness of the Monge-Ampère's eigenvalue. So I will talk about a quick proof of the uniqueness. So in the uniqueness, we need two ingredients. One is the integration by part, and another one is called the mixed Monge-Ampère inequalities. And so it said the following: suppose that you have n convex function, u1 to un, and for each one, you can have, you compare the Monge-Ampère measure of ui with respect to the fixed reference measure nu, and suppose that is not smaller than fi. So it means that maybe you just put the equality here for the first reading. So suppose that fi is the Radon-Nikodym derivative of the Monge-Ampère measure of ui with respect to the reference measure nu. Okay, so this is the way to read. Then suppose that all the fi, the density here, I just add 1 with respect to the measure nu. Then if we look at the mixed Monge-Ampère measure of the function u1 to un, then you can have a lower bound, and in terms of the reference measure nu, and the density here is just given by the product of the n root of the density of all fi. And so actually, when all the function ui are C2 and the measure nu is just the Lebesgue measure, and you have the equality here. This inequality follows from the Gaussian inequalities in his studies of the hyperbolic polynomials. On the other hand, so in the complex version, this comes from the works of Dino. So I think the proofs are almost the same. By approximation by smooth function. To keep in track of that, we are not working with Lebesgue measure, but we work just any Borel measure. All right, so let me indicate the proof of the uniqueness of the Monge-Ampère eigenvalue in the finite energy class. And so the statement said the following. So suppose that you have two numbers, positive number, capital lambda, little lambda. Capital lambda is the real Monge-Ampère eigenvalue, and little lambda is the sub-eigenvalue. And you want to say that the eigenvalue is not smaller than the sub-eigenvalue. And so all the functions involved here are in the finite energy class. So this is crucial. And so how to prove this? So first of all, we do the integration by part, which one slot here, because all functions involved are just in the finite energy class. And so therefore, with the absolute value of V, we just think of negative V. And so therefore, we can move one U from inside out here, and we can plug in V to the inside. And so therefore, this is the formula. On the other hand, we just use the fact that the mixed Monge-Ampère measure of entropy of U is the Monge-Ampère measure of U, which is capital lambda to U to the n times U. So this is what happened to the left-hand side here. For the right-hand side, we just use the mixed Monge-Ampère inequalities. And so all the functions have the reference measure nu here. So we just apply this mixed Monge-Ampère inequality. And so if we put everything together, from here to here, and this is what you get. And so if we compare both sides, we see that the power of U and V are the same. And so the only difference is in the constant, and the constant here lambda, but here you have certain power of lambda, certain power of capital lambda, and because all the functions involved are non-zero, and so therefore this gives us a quick proof that capital lambda is not smaller than lambda. So it's very quick, just use the integration by part and the mixed Monge-Ampère inequalities. And so this is the case of uniqueness in the finite energy class. Okay, so we might wonder what happens if we consider the Monge-Ampère eigenvalue outside energy class. Of course, the first question is it possible to have a measure nu outside energy class? By the way, when nu is integrable with respect to the distant function, then of course we have the uniqueness that I mentioned. And so the one that's integrable, you can think of like the negative power alpha of the distant function when alpha is smaller than 2. And so now it's not surprising that we have the number negative 2. So that's the power that never worked for our assumption. Because and we look at a very simple domain from the negative 1 to 1. Okay, so this measure nu here only has singularity at the boundary. And so, of course, let me say a few words about the finite energy class before I say the example. So for the finite energy class, so somehow if a convex function in a finite energy class, that function should have a Holder regularity C1 over n plus 1 to the boundary. And actually, it's a little bit more than just a little bit more than this. And so therefore, if in one dimension, when n equals 1, then if your function, you have any function which is not only C1/2, then usually it's not in finite energy class. And therefore, maybe we don't have the integration by part, and what's the consequence? Maybe we don't have a uniqueness of the Monge-Ampère eigenvalue. And of course, in one dimension, the Monge-Ampère eigenvalue problem is just the second order, usual eigenvalue problem. And so it turns out that even in this problem, in one dimension, with the measure nu quite singular, we can have families of eigenvalues called lambdas. For each alpha is smaller than 1/2, we have an eigenvalue lambdas alpha exactly these quantities with the eigenfunction written by this form with zero boundary condition. And so therefore we have a family of eigenvalue. And furthermore, we see that when alpha is exactly 0, this quantity is just negative 1 minus x squared to the 1/2. So it just fails this condition. And actually, you can compute when alpha equals 0, this function had infinite energies. And so, on the other hand, when alpha is non-zero, we see that, let's say, when alpha positive, we see that we had a double more when you are approaching 1. Because when alpha positive, this function is holder continuous of order less than 1/2 because of the divisor over here. And so therefore, what does it mean is that if we look at this one, we can check that all these functions are also convex. And so therefore, in this eigenvalue problem, we have a family of eigenvalues. And for each eigenfunction, lambda's absolute value of alpha, when alpha is 0, we have two eigenfunctions, v of negative alpha and v alpha. And so they're not uniqueness in terms of for each eigenvalue. And furthermore, we see that our domain here is quite symmetric, which back to the origin, but the eigenfunction for each class is not symmetric. And so we also have symmetry breaking. We also had a non-uniqueness of the convex eigenfunction. And so somehow the finite entity class seems to be the threshold that when you are there, everything can be unique and a lot of nice property, but when you're below it or just barely misses, then a lot of wire thing can happen. And so I can say that this is something very reminiscent of convex integration in fluid dynamics. All right. So now.
Can you say more about that? What does this have to do with convex integration?
So I just said reminiscence is not exactly, because somehow convex integration, they're just approximating this exact solution. So this is quite different. So because in convex integration, we will construct a lot of solutions when you are below certain energy threshold or something like that. So
they use limiting processes.
Yeah, yeah. But this is exact solution. There's no limited process in this. All right. So let me talk about the second theorem when I consider the degenerate equation when the P is smaller than n, and we can allow the measure nu to be more singular. So, but we need this integrability condition. It turns out that this weight here is critical in the sense that if we just solve the direct layer problem with the measure nu n, and if we just have this bound on this integral, then somehow we lose the compactness. So this is one specific example in one dimension when we can construct explicitly the nu m and then the um. So this is nu m is just the second derivative of um here, and we can compute that all the function here. If we weight the second derivative, again, the distant function, they have energy bounded by 4, but all the measure here, they convert to 0. But for 0, the relay problem gives you 0 solution, but um here do not convert to 0. And so somehow this measure here is kind of critical. On the other hand, if we put the distant function to the power of gamma when gamma is more than 1, then we have compactness. So I might explain later on in the talk. So the one with the exactly power 1 is critical.
Wait, which limit are you looking at here when you talk about distant?
So this limit here is in the sense of conversion of Radon measure.
M to 0.
I'm going to infinity.
Infinity.
I'm going to infinity. Yes. All right. And so, so we see that the non-compactness issue when we would like to solve our problem. So therefore, one way to handle all kind of difficulties is that because we only have the issue at the boundary. So one naive way is to try to truncate the measure nu by some finite distance away from the boundary, and thus with the new measure nu m. Now, okay, and we go into infinity again. And so with that, we can try to solve the corresponding in the finite energy class because we have no issue with the mass at the boundary for the new n. And so what's saved the day is that during this process, we have a lot of monotonicity. And so how that works, so because we will use one tool, it's called the uniform Aleksandrov-Jerison maximum principle. That's I will explain that too. And so this proof of this new maximum principle based on a refinement of Blocki maximum principle for the mixed complex Monge-Ampère measure. And so do we have 15 minutes or I have to stop now?
Maybe not.
10 minutes?
Yeah, sure.
Okay, thank you. Okay, thank you. All right. So this is the Blocki time maximum principle. It's basically said the following. Suppose that we are working in a domain omega, do not need to be convex. But if suppose we have two convex functions v and w, satisfy one function is lower than the other, and with the same boundary data, and we want to see how can we estimate w minus v. So assumption w minus v is positive, and so we can do that in the weighted way. If we test again to all the mid-Monge-Ampère measure of convex function u1 to un, then we can estimate the weighted difference of w minus v in terms of the difference between the Monge-Ampère measure of v and w. And so here, all the functions u1 to un are just boundary convex functions which are non-positive. And so this is the version that Blocki proved. In his proof of the complex Monge-Ampère setting, there is no, he did not subtract this term. Because in his proof, he just have the full term like this. So it becomes very, very positive. But in here, we have a very refined argument that it says that when the measure of v and w are very close, then this weighted estimate can give us a very refined estimate for this difference between w and v. And so this is the new tool.
Is it obvious that the right-hand side is positive?
It's not obvious. Exactly. That's one of the hard work. There's some other work before that. So at this, for this writing, it's not obvious. Exactly. Thank you. Yes, you're right. It's not obvious. Anyway, so what's the interesting point? The interesting point is in application, we will choose proper function u1 to un. The way to do that, because we want to turn from the weighted estimate into the pointwise estimate. And so one way is to make the mixed Monge-Ampère measure to be the Dirac mass. And one way to do that is look at the cone-like function. And one way to do that is that actually if you have a perimeter alpha to play with, and let's say alpha from 0 to 1, and actually one way is that we look at the function u at the point here. So this is the graph is like this. So it's cone-like, it is 0 on the boundary and it's at the cone. And if we choose properly, then it turns out that we have a new estimate, the pointwise estimate. And so it says the following. Suppose that we are given the two convex functions, v and w, 0 on the boundary, and the Monge-Ampère measure of v is above the Monge-Ampère measure of w. And so therefore, for any perimeter alpha, a constant between 0 and 1, and any point x0 in the domain omega, we can estimate the difference between w and v. Because this condition already allows us to use the maximum principle to say that this quantity is negative, but we want to estimate it, and we want to estimate this. There are two quantities. One quantity is the distance to the boundary, another quantity is the weightage of the difference between the Monge-Ampère measure of v and w. And so in this case, we see that so this is the way to have the estimate, and this actually turns out to be a well-known estimate when w equals 0. When w equals 0, we don't have this subtraction here, and so this was come from the work of Aleksandrov when alpha is equal 1. When alpha is equal 1, we don't have the weight in the integrand, but we have the distance to the boundary outside here. On the other hand, when considering the Minkowski problem, Jerison, about 30 years ago, have a version of the theorem when w equals 0, when alpha is bigger than 0. So when alpha is bigger than 0, this is non-zero, but this is the power is less than 1. And so somehow the work of Jerison have the dependencies of C in terms of alpha, and we are not sure whether we can take alpha to go to 0. The interest of the theorem is that we can take alpha to be any number from 0 to 1, and the estimate here is uniform in alpha. And so therefore, quick back to the equation that we will study when the measure, if a measure had the integrability condition with respect to some distance to some power smaller than 1, then we'll use this one because we can take alpha to be positive, we have already compactness. But in our case, we can take alpha exactly 0 because that's exactly our condition. All right. And so, all right, so I have about 5 minutes, so let me quickly mention how to apply the estimate here to solve the degenerate Monge-Ampère equation by monotonicity. So we see that our interest is to take alpha equals 0. And so this is the version of the estimate that we need to use. And furthermore, when p is equal to 0, and this is just the Dirichlet problem, and we truncate the measure nu from a small distance from the boundary. And so therefore, we would like to apply this estimate for different value of u equal um prime and um, because u and um are the solution for the Dirichlet problem with the truncated measure. And because we have no issue at the boundary for the truncated measure, we can have the solution un. And so therefore, if we apply to this one, then we see that this is very helpful because although we have the issue with the compactness, if we don't have the subtraction, but now all the measure nu m and nu m prime, if we plug into this formula, somehow that's a tail estimate. And the tail estimate, because we have the integrability condition on V, the tail estimate gives us the compactness. That exactly gives us to pass through limits when m goes to infinity. On the other hand, this argument does not work when we do for p bigger than 0, because when b equals 0, the measure we truncated had a monotonicity, but we also have some quantity involved in the solution. We don't have any information about that. And so therefore, it's not sure whether we can have the monotonicity with the new measure, with the way given by the p power of un. It turns out to be okay when p is more than n, because this is a new comparison principle for degenerate subcritical Monge-Ampère. And so, roughly speaking, it's the following. Suppose you have two convex functions. One equal V, it is a subsolution in this sense to our degenerate Monge-Ampère equation. Another one, it is a super solution. And we just require that u is equal to 0 on the boundary and V non-positive. So therefore, the super solution is above the subsolution on the boundary. But we will need to require that the subsolution is negative, which is okay, because in our setting, when we look at non-trivial solution, this is the condition that we have. So what is the requirement on the measure nu? We can prove the comparison principle that this super solution is above the subsolution in two settings. Either the measure nu is compactly support. That is exactly the case that when we do the truncation measure, or it had the density which is continuous and strictly positive, I think Frick just asked at the beginning. And so therefore, under either one of two conditions, but the most relevant one is the one with the compact support measure, and actually the super solution is above the subsolution because everything negative, so therefore the absolute value of u is also smaller than the absolute value of v, and so therefore we now transfer from the inequality here into the inequality for the measure of u and v. And I think this is a good time to stop. Thank you very much for your attention.